Good morning. Just a reminder that if I use a highlighter, that does not mean that you have to highlight the same thing. That's just the way that you can see what I'm talking about at the moment. And if I write something, I'll try to remind you whether to write it or not. That way you guys aren't writing something down and then being confused on whether you were supposed to write it down or not. So the topic/objective for today is that I will be able to turn a complex fraction into a simplified fraction and comprehend that they hold the same value. So by the end of these lesson notes, you will be able to look at a complex fraction, which we haven't defined yet, but we will, and then simplify it down. And then the essential question is, how does one properly read a distance versus time graph? We're also going to be looking at some distance versus time graphs that we also need to be able to understand in order to be able to solve some of these problems. So let's start off with some vocabulary. A complex fraction has at least one fraction in the numerator, denominator, or both. You may need to simplify / divide complex fraction when finding ratios and rates. So an example of a complex fraction, and I do want you to write this down over here in the side notes. So an example of a complex fraction is something like maybe, let's say, 1/2 over 3/4. So it's a fraction in what's already a fraction, because we have our fraction line here, and then we have two fractions, one on top, one on the bottom. And so if you see a fraction within a fraction, that's called a complex fraction, because it's pretty complex. But it's actually very simple to simplify it down. So we'll be working with simplifying it down in just a little bit. Let's go ahead and take an example of where we would actually use this kind of complex fraction. So in example 3, we have that the graph shows the speed of a subway car. Find the speed in miles per minute. Compare the speed to the speed of the subway car in example 1. So we've got this graph here, and we're going to have to understand how to read it before we actually are able to analyze it. So as you can see, we have an x-axis. That's the one that travels horizontally. You can remember horizontally because the sun rises on the horizon, and the horizon is considered left to right. And then you have on the y-axis is the vertical axis, you have distance in miles, and then on the x-axis you have time in minutes. So what this means, what this signifies, is that as the time increases, you can see that the distance is increasing also. So as the time that the subway car is traveling, the distance that is traveling also increases, and that seems pretty logical. So that's why you see this line here is representing the time and distance of the subway car. And as you can see, we have some points that are highlighted too. You don't have to circle this. We have some points that are highlighted. And so those points we can read off of this graph in order to determine some information. We can determine from the point that the time that it's traveled and the distance that it's traveled, because that's what these x and y coordinates mean. And so we need to ask ourselves, a good question to ask ourselves is, which represents the value of x and which represents the value of y, or what represents time, what represents minutes. And we'll put a note here in our questions, not really a question, but just a note. We'll put it into a question. In a coordinate plane, which value represents the x value, and let's make that coordinate point. Which value represents the x value and which is the y value? And you might already know the answer to this, but if you don't, it's something good to note. So these coordinates are set up, always will be set up as x, comma, y. So that first coordinate that you see, that's going to be your x value. So here we have our 1/2, that refers to the x-axis, and it means that half a minute has passed by. And then the y value, our second point, the 1/4, that's referring to the y-axis, and it means that in that half a minute, it's traveled a quarter of a mile. So the coordinate point, let's put that down, the coordinate point 1/2, 1/4 signifies or means that in 1/2 a minute, so in half a minute, the car traveled a 1/4 mile. So the coordinate point 1/2, 1/4 signifies that in half a minute the car traveled a 1/4 mile. And so we can also now analyze the second point and analyze that 3, 1.5 means that in 3 minutes the car has traveled 1.5 miles. And because we know the distance and the time, we're able to find the speed, as question 2 is asking. So we already chose and interpreted the point on the line. We said that 1/2, 1/4 means that in half a mile, it's traveled a 1/4 mile. In half a minute, it has traveled a 1/4 mile. And then the second point, in 3 minutes, it's traveled 1.5 miles. Now we need to find the speed. And so it gives us the formula, distance traveled over elapsed time. So we can put distance over time, and that is going to be equal to our speed. And so we can use any of the points that we'd like. So let's go ahead and use that 1/2, 1/4. Let's start off with the first point. And so we're going to set this up as distance over time. So that's the y value over the x value. Because remember that y value represents distance and that x value represents time. And so if y, we're going to set up as y over x, we're just going to take our coordinate points and we're going to plug them into our formula here. So it has traveled 1/4 mile in half a minute. But this is a complex fraction. We don't really say that, we're not really going to tell people, oh, how fast does a subway car travel? It travels 1/4 mile every half minute. That doesn't really seem simple enough to state it like that. And so that's why we need to simplify this complex fraction. Well, we can actually simplify this pretty easily, because if you remember that a fraction, or this fraction sign, is actually a division operation, then we can set this up as 1/4 divided by 1/2, and 1 divided by 1 still equals 1. 4 divided by 2 is 2. And so now we just simplified this down to say that every 1 mile, because mile still is on top, it takes the subway car 2 minutes. And we can simplify that even down further. This would be considered a rate. We could simplify that down even further to a unit rate by dividing 1 by 2 and saying that the car will travel half a mile every 1 minute. And so using this graph, we were able to set up the formula for speed, which was given, plug in our values, and then simplify it down to find not just the rate, but we can also find the unit rate. So the rate of the car is that it travels 1 mile every 2 minutes, and we simplified that to a unit rate, saying that it travels half a mile every 1 minute. And we could have also done that for the second coordinate point. I do want you to write it down. So with point 2, we also could have set it up as 1.5 miles every 3 minutes. Simplified that fraction down. There would be 1.5 divided by 3, which we can write as 3/2 divided by 3 over 1. 3 divided by 3 is 1. 2 divided by 1 is 2. And you get the same rate. You get that it travels 1 mile every 2 minutes, just as we got up here in this rate. And that makes sense because it's still the same subway car, so we shouldn't get a different rate. And so our unit rate will also be the same in that case. If our rate was the same, therefore our unit rate will also be the same. It will also be traveling half a mile every 1 minute. And if you look just a little further, we can confirm that we did the calculations correctly, because it does tell us that the speed of the subway in example 1 was half a mile per hour. Okay, so before moving on to the next problem, the on your own problem, you can watch the next video. I'll have that on your own problem